It's been almost 2 years that I started with the company, almost 3 actually right now. I'm part of the core team for the moment, transitioning to product management, as I said, where my current work is mostly with networking, input and output, inter-process communication, threading, and 2 classes. As you can see, threading is one of the things that I work mostly on. I kind of like the low-level details and the structure of how processors work. This is what I'm going to be talking to you about today. Other duties I have at Qt Software, I'm the liaison to the KDE community. Originally, actually, I'm from the KDE community, where I started in 2000, so it's been several years for now. And I'm also the release manager for Qt. So I'm the person responsible for producing the packages that you guys receive and the open source community receives. Well, enough about me. So I'm going today to be I'm going to give a brief introduction on the threading subject, talk about how it has evolved in Qt, and then we'll show you APIs, do's and don'ts, maybe some tips and tricks that you can also use. Let's move on. In general, people advise against threads. Why is that? People give many reasons why not use threads. Think about it. People say threads make the program more complex. It makes your program behave erratically. It makes your program, for instance, not be deterministic. Maybe some people are exaggerating, but they're also right that they do make the program more complex. So think about it. If your program doesn't use threads, you don't have to use it. It doesn't need threads, you don't have to use it. Right? There's this comment from Alan Cox attributed to him. I'm not sure if it actually came from him, but everywhere you look on the internet for this phrase you see associated with his name. He was discussing on the Linux kernel and he said, threads are for people who can't program a state machine. Yeah, maybe he was exaggerating. State machines are also not easy, but in some cases threads are needed. Today what happens is that we have desktop processors with multiple cores, dual cores, quad cores. The new Mac machines that you can buy and we have in the office, for instance, are dual quad cores. They have eight cores. That laptop, for instance, is a dual core, and this is not a very high-end laptop. It's a normal laptop you can buy, and it's a dual core. That means you have more than one processor available. Of course, you have more than one application running at the same time. But if your application has enough of a complexity that it could use more than 100% of one CPU, it's actually very useful to use it. And embedded hardware will follow very soon. That means we will probably be seeing soon hardware for embedded devices like phones or probably more high-end like PDAs that have more than one core or more than one processor even. To use all cores, you need threads. That's the only way that you're going to, your application, make use of the available processing power. And to use threads, you need to identify tasks. You need to identify the relationship between the different operations that your program has, and you have to divide them into several different tasks. As I showed in this small example, 3 threads and plenty of tasks, most of them running on one thread. That's normal. But there are a couple of them that might be useful to run on separate threads. So, why separate threads? What can you use threads for? What do you need threads for? I came up with a couple of items that we might think about. For instance, time-consuming tasks, because they will take time to finish, and you don't want to block your application's main interface to the user while you're doing that operation. You separate it into a separate task where it will be run, and then when it's done, you get a notification and you update your interface accordingly. In the meantime, the main interface is still responsive to whatever input the user has. Other reasons are blocking operations. For example, if you have to call a library that does not have an asynchronous interface, you will want to use a thread, for instance, because then that call, which doesn't take CPU time but doesn't return immediately, will process in parallel until it's finished, and then you get your notification. And there's obviously the parallelizing of independent operations. If you can divide your task in multiple separate tasks, subtasks, then you can parallelize them, depending obviously on the case. But this is one example. There are obviously more. There are obviously more cases where you can use threads for. I'm going to take some time here to talk about one example that has always appeared to me in Qt tasks, which is an example of where you don't have to use threads for. People always say they have to use threads for the sockets. That's not entirely true. I'm afraid actually what happens is that people think they need to use threads because they're coming from a Java background. I'm not sure, but it seems so because Java does not have asynchronous sockets. So every operation that you do, a write or a read, might be blocking. That's not the case in Qt. We made our socket classes be asynchronous. So all you have to do is write and then return to the main event loop of your application. Or wait for signal saying, here's more data. Feel free to use it. So, yes, sockets are not, you don't need to use threads for sockets. I'm raising this issue exactly because, like I said, many tasks come from users on the Qt interest mailing list or even through our support department that have problems with threading and socket classes in Qt. And I don't think any of those applications that I've seen have enough high data load to warrant a thread. So people are just using it because they think they have to. Maybe this is a case to think about. You don't really have to. So, let's move on. I'm going to show quickly what happened about threading in Qt. In the beginning, there was nothing. Qt 1 had no support for threading, none at all. The entire library was unsafe for threading. But then again, that was 1994, 1995, a few years later. Threads were new. Most operating systems had little support for it, especially Unix. Little to no support to it. If you think about it, POSIX threads didn't come to Linux until glibc 2.0, which must have been 1999, 1998. So people didn't expect threads there. But by Qt 2.0, we had QThread. That was an entirely new class. Fancy new stuff. Here there be dragons, be aware. So it was not enabled by default. You could choose to enable it, and it would do some changes to the Qt library, meaning it would be multi-threaded. Qt 3 made that by default. So if you remember Qt 3 times, you'll remember that the library that was previously known as libqt changed to libqtmt, where mt meant multi-thread. Actually, the same thing was possible in Qt2, but like I said, it wasn't the default. You had to enable it. Qt3 had it by default, meaning that you could use QThread to create your threads and do your work there. But what happened was that Qt3 did not make threads really first-class citizens. You could just do your own tasks in there, but you could not use Qt in those threads, which meant that all the nice stuff we had for Qt was confined to one thread. Qt4, however, made threads first-class citizens. First things was that the tool classes became reentrant. QString, for instance, was reentrant. I remember talking to a developer friend of Amarok. Amarok is the music player for KDE. Maybe you have heard of it, maybe you've actually used it. What he told me was that he had these weird crashes in Amarok because they were using threads, and it was really unexpected. They did not see the pattern until they realized that in Qt3 they were using QString in multiple threads. So they just took one string, copied to another thread, and were using it. But then suddenly the program would crash. And the reason for that was that QString was not reentrant, was not thread safe. So one thread would mess up the other. This we fixed in Qt 4.0. Tool classes became reentrant. QList, QVector, QByteArray, QString. All the tool classes. We started using thread safe atomic detaching. Weird words. That meant that we would use implicit sharing to save memory. But in order to accomplish the implicit sharing and be available in multiple threads, we would have to, when doing the copy on write, separate atomically. How we accomplished that, I'll go back into it later on when I present the atomic operations. But another thing that was interesting was that we added the possibility to have event loops in auxiliary threads, not just on the main thread, not just the Q application exec. So you could actually call in your run function, you could call exec and expect to receive event loop related information. So for instance, obviously events, but also socket notifications. So socket classes were usable from other threads. And this cool new stuff that we invented, the cross-thread signal slot connections, meaning that you could emit a signal in one thread and receive it in another. This is actually so interesting. I'm going to explain quite quickly how it works. So the old case was signals delivered immediately. That's the so-called direct connection. But we invented the queued connection, which is how the cross-thread works. When you emit the signal, Qt will copy what you passed on as arguments using the QVariant class, which actually means you can extend it. You can extend QVariant to support your own types. So Qt copies those arguments, puts it into a list, and posts an event to the receiver object. But like in Qt3, events were already thread safe. And with the advent of event loops on the other threads, what happens is that those events were processed in another thread. So the other object, the receiver, receives those objects, those signal emissions in the other thread. In Qt 4.3 we invented the blocking queued connection, which is basically the same as the queued one, except that we wait on the sender side until the receiver is finished. So there's a thread synchronization primitive there. Actually it's a queue semaphore. I'm not going to go into details about it. If you want, can talk to me after the presentation and we'll discuss. Or you can email me actually. But that was not all. Qt 4.4 brought threading to a whole new level. The atomic operations that were the basis of the reentrancy in the tool classes, we made them public. We made them documented. We added a few new classes abstracting thread manipulation, because threading should be easy. We added QtConcurrent, which is an entire framework for doing operations in parallel. I'll present some of it in the next section. We also made some enhancements to existing classes that had nothing to do with threading. We allowed painting from multiple threads, as long as you're not touching the windowing system. So you cannot do painting to a QPix map, because that goes into Windows or X11 or even Mac. But if you paint into a QImage, which is a device-independent paint device, you can do it from any thread. Interesting thing is that you can also use a QPrinter. So you can actually start printing in the background. You can do text rendering on X11, which wasn't possible before. It depends on underlying library support, but it works. There's also thread-safe rich text and SVG support. Combine all these three together, that means you can actually start printing in another thread. Why is that useful? It means that your application can, your user, for instance, goes and clicks print. Your application in the background starts generating the print job. Might be an easy operation, might not be. It depends on your application, depends on how much processing you need to produce the printing. But since it's being done in a thread, you're not blocking the main interface of your program. So you don't have to show this annoying dialog box, printing, page 1, page 2. The user can continue working. Let's move on, talking about API do's and don'ts, maybe some other tips and tricks. I divided into two sections, talking about threads themselves and Qt Concurrent. This is where I'm showing a taste of the API. And then I'll talk some more about locking in Atomic. I'll come to that later. So, things to remember about QThread in Qt 4. This happens to everyone, including me. Yes, I've made those mistakes more often, more than once. The QThread object is not in the thread. Weird. That happens that, think of QThread as the manager object. It's just a wrapper around the thread. So you have the object and the thread. Don't think of them as the same thing. Think them as separate. Because the object belongs to the thread where it was created. Meaning that if you post an event to it, or including a meta signal where it's connected to, it will be received in the thread that originally created it, not in the thread that it is managing. It's important to realize that, because my simple case was that I just had a single shot timer saying quit. But what I had forgotten was that that quit comes in a different thread. So my process was actually not safe, because the event that I was expecting was not run in the thread where I wanted it to. Be careful. Also be careful because the constructor is run in the original thread. It's easy to think about it. You have not called start yet. If you have not called start yet, your thread is not running. Therefore, the code that you're running there is wherever it was before you started your thread. Like I said, be careful with signals and slots. The event loop is also not automatic. When we had discussed that Qt made event loops possible in QThread, it means you actually have to call exec. Many people forget that and they do some kind of blocking operation on the thread. And then they expect events and signals and slots to work, and unfortunately they don't, because you did not call exec. So if you need those events, be sure to call exec when you're using it. So, small code sample. This is a one thread. On the left side, a class I call myThread, which basically does is re-implement the run function, and there you put your code. And somewhere else, in a function I decided to call somewhere else, you create this new thread object and you call start. Simple. This is basically what you have to do to start a thread. But what if you needed a thread, any thread? You don't need it to be the specific thread. You don't need a thread to be running all of the time. Maybe you just have this task that you want to be run and it finishes, so you don't need to keep resources up. So basically what you need is a QRunnable, something that can be run somewhere in a thread. So you can see that it's very similar to before. I'm going to go back and forth so that you see it. Here's the thread, here's the runnable. It's almost the same thing. And your function, you're somewhere else. You basically ask a thread pool to start it. Here's an interesting thing. There's a global thread pool. So you can simply ask the Qt to say, I don't want to keep track of my thread pool. Just start it for me. I guess this is actually simple enough. Not very difficult. So here's a list of comparison between QThread and QRunnable. QThread derives from QObject. It has signals and slots. On the other hand, QRunnable has no base class. It's a simple class with a virtual function. And therefore it has no signals and slots. So on one hand you have signals and slots. On the other hand, QObject is a heavy class. I don't know the exact figures, but it goes upwards of 200 bytes for every single one that you create. QRunnable, on the other hand, is very lightweight. There is also another cost associated. When you call start in a thread, the operating system has to allocate resources to start that thread. So there's a cost associated with it. Some systems are fast, some are not. So you have to put those things in the balance on the scale together. QRunnable, on the other hand, does not require, maybe it does, but the point is it doesn't have to be that specific thread. So what it does is that it runs on any free thread that might already be running on the pool. If there is none, then one is created. But if one is free, there is no cost associated in creating it. And it's a new class in 4.4. But here's another tip. What if you just need to run a function? You have the function, but do you have to create a QThread or QRunnable for it? No. QtConcurrent has this function called run, which takes as argument a function pointer. So all you have to do is call it run, and then at some point or later you can call wait for finished. Or you can even not call and just let it finish on its own. You can see that the return argument is QFuture. It's a nice name. Futures are an invention. I don't remember which language it came from. Futures are a concept coming from other languages. It's a result that doesn't exist yet. It will exist in the future, therefore the name. So the return argument QFuture represents an asynchronous computation that might or might not still be running. It might not even be started yet. So QFuture has useful functions like is finished, is running, or is started, because it might not have even started, it might have finished, we don't know. And it has a function called wait for finished, which allows you to synchronize the result from future to your other code. And it's a template function, which means you can actually receive different arguments as return values. As we saw in the previous example, my function returns int, and QFuture is an int. Actually, there's more. QFuture is actually part of a family of functions. It can be combined with QFuture synchronizer. I just gave you an example there. That means you can actually put two or more, actually one or more futures together and wait for them all to be finished. I guess you can see how that could be useful. But you can also use QFuture Watcher, which is a class deriving from QObject. And there you receive asynchronous notifications in the form of signals and slots. The example I put here is just basically to wait for the finished signal in a different slot. So you can continue your operation and then later receive it. More nice new stuff. You can actually pass arguments to the functions. Here you can see that the function myTask receives a string argument, and that value is the 42 we have on the right side. The return value is an int, which we receive on the future. And we can actually pass arguments from a list. QFuture looks like one argument, but if you look at it in the documentation, you can see that it actually supports multiple, a list, a homogeneous list. So with the help of this function called mapped, we pass a list of arguments to go to the task function, and that task function is then called once for every entry in the list. How that could be useful? What queues could we have for list of arguments? Think about it. Many times you have a list of tasks to do. For instance, let's think of image processing. You want to create a thumbnail from your vacation photos. You have, I don't know, if you're like me, you took 300 pictures during a weekend. That's actually a time-consuming task, and you have several cores at your disposal. So basically what you have is an input, a list of files, and you want to run this function which does something to the pictures. This is an example of how it could be useful. Not only that, you can receive returned arguments. So your input could be a QImage and you receive a QImage. But it can be different things, as my example here shows. There's this memory function called results, which returns a QList of the values. More than that, the watcher has signals saying entry number 1 is finished, entry number 2 is finished, entry number 3 is finished. So you can actually tie that together with a progress bar showing the progress of how things are finishing in your application. I hope that was interesting. You can find more about QFuture in the documentation, obviously. I'm not going to go into more details about it because it's not very easy, but it has lots of features. And you might want, and I don't have 3 hours to explain them all. So moving on to the second part of the API, locking and atomic. The problem is simple. You have some global data, and it must be protected because it's accessed from different threads. or different tasks even. So in order to use it, to access it, to change it, you need to ensure that other threads are not using it. The example here I have is showing just a mutex. So what it does is that task 1 creates calls lock on the mutex, uses it, and then unlocks. Task 2 is slightly more clever. It uses this helper class called QMutex locker, which basically is the same thing as the one before, but it automatically unlocks when you're done, when you reach the end of the function. That's actually a point of synchronization in applications. What happens there is that if multiple threads are using the same global data at the same time, then they all have to wait and go one after the other. Think of it as a crowd coming out of the underground. So think about the last time you took the underground, and then there's this escalator going upwards. And there's this crowd coming to the escalator, and they have to go one after the other. If you remember that example, you actually remember that it's quite annoying. It takes a lot of time, depending on the case, for you to get from where you are to the escalator. We can improve a bit by using a read-write lock. That rests on the premise that when you're reading it, when you're reading our global data, you're not changing it. It rests on the premise that the reading from the data is thread safe. Be careful. Qt2 classes are like that. So you can use a read-write lock to protect a QString, a QList, a QHash, for instance. But maybe it's not safe for your own data. You have to think about it before you use this. It has, like my example shows, lock for read, lock for write. The difference between them and QMutex is that lock for write is like QMutex, so only one at a time, but lock for read is many at a time. Like I said, reading is thread safe, that's the premise. Therefore, many can read at the same time. I don't think I can come up with an analogy for it. But sometimes no locking is necessary. Here's an example of operation that can be atomic. No locking is necessary when the operation that you're doing on one thread does not affect the operation on another, or if your operation is ensured to be atomic. The problem with thread safety is when you're trying to modify one object and another is, and your thread during the modification is interrupted by another. So that other thread sees an incomplete state. And therefore, your first thread, when it returns, might not receive the object that you were looking at in a consistent state. That usually leads to crashes. But atomic means it cannot be divided. It's one operation that cannot be divided in two. This example here shows a simple counter. The task 1 adds 1, fetch and add 1. Task 2 simply takes the current value. The on the tasks is a simple counter here, probably finding out how many tasks are running at a time. And the ID that the function caught in the beginning was used for something. Let's think of this case. The standard guarantees, or most operations guarantee, that operations on small integers are actually atomic. So incrementing, decrementing, using the value, or comparing, those are atomic operations. So you ensure that when you take that value, it will not be in an inconsistent state. So why can't you use int in this example? It's the same as before, except that I'm not using QAtomic and the fetch and add operation. Why can't you use this one? Some might say because it's not, the compiler might generate invalid code. It doesn't know that you can do that. It doesn't know that another thread is using that counter. You're right. So we add this keyword called volatile. Is that enough? The volatile ensures that the compiler will always reload the value, meaning that it ensures that what it's showing you when you use it, if it was modified by another thread before, you're going to see that value. This example is still not safe. Can you spot why? I said operations on small integers are atomic, each operation. But if you look at the first line of task 1, there are actually 2 operations. One of them is increasing the counter. The second one is taking its value. So this example shows that there is one operation that you thought might have been unique, atomic, which is actually 2 steps. So you first increase and then you take the value. This is where QAtomic helps you. There are 3 operations that we support: test and set, fetch and store, fetch and add. So let's start with the simplest one, which is fetch and store, basically called exchange. Think about Hollywood movies. What does the villain do when he has to steal, or even actually the good guy, when he has to steal a precious item of high value in the safe? Usually they have those pressure safes where if you touch it, the alarm goes off. So what he does is that he has the item there, and he has a bag of sand, and he does atomically switch. Take one, put the other. The processor is actually more smarter than the villain, because it does this atomically. It guarantees that no other thread sees the state in between. So actually it takes one value, puts the other in one step. The second operation is actually called test and set. So the villain comes to the vault, and there's the item. So what he does is that he looks at it and says, this is the good one, and then he does the exchange. However, what happens if when the villain comes, somebody has already exchanged the item? So he looks at it and says, this is a bag of sand. I'm not going to do my operation. So the test and set operation is actually the equivalent of that. It compares what you have in your destination with what you want to exchange, and if it's equal, then it exchanges. So it's a compare, if it's the same thing, and only then it exchanges. The final one that we support is called fetch and add, which you can think of as a specialization of the first two. What it does is that it takes the previous value, adds something, and then replaces it in one single step. You can think of it as fetch and store. You take the previous value, add, and then exchange. But not only that, because the taking of the value and adding might not have been atomic. So it's actually based on test and set to make sure that we are actually doing the right thing. Each operation, not only that, is supported in 4 memory ordering semantics, if the hardware supports it. I'm not going to go into details of that. This is a level 3 presentation. If I went into memory ordering semantics, we would go level 4 or 5 or even above. Suffice to say that there are 4 of them, called relax, acquire, release, and ordered. You're going to find more information on the Qt documentation, and you can rest assured that if the hardware doesn't support that specific ordering, Qt uses the next step on it, meaning something that's more strict, never less strict, but not overly strict. QAtomicInt is actually very useful for reference counting. So useful that actually we have API for it in it. It's actually the basis of our tool classes. So when we look at QString, QList, and what I said before about the atomic detaching, this is how we implement it, via reference counting by atomic int. QAtomic also allows you to test both at compile time and at runtime what your processor supports. Some processors support a lot of things, some support different. So the 2 tests that you can make is either whether the operation is native or if it's emulated. If it's native, it means your processor supports that operation. Emulated means somehow it's emulated, probably by the operating system ensuring that no other threads are interfering. It's easy to see that a native operation is probably cheaper than emulated. There's also the other test, whether it's wait-free or looping, because some processors do not support the atomic operation. So actually what they support is a subset of the operation. So you actually do, for instance, let's take the example of fetch and add. You take the previous value, you add, and then you replace, as long as the value that you're replacing was the value that you had thought. But if something else interfered, then it redoes the operation. It redoes. So you can see that looping could mean a long time in some processors. Qt actually supports, on some systems, yielding the processor, letting other tasks and other threads to continue. The problem this is alluding to is called priority inversion. You can find more information on priority inversion on the internet. On the other hand, if it's wait-free, that means it's actually constant time, meaning you're sure that it's going to end in a finished exact amount of time. That was it. I'm going to hope that you liked it. So, analyze your problem. I presented threading. I presented lots of things that you can do with Qt, but analyze your problem. Can your problem be solved without threads? For example, signals and slots. This is the case of the sockets I mentioned. So you can actually program a state machine, and Alan Cox will not be disappointed in you. But we think that threading should be easy. So if you analyze your problem and you decided that, yes, I need threads, then we will give you all the necessary tools to do it. The API is there and constantly being improved, meaning we will always add more things to make your life easier. Threading should be easy, meaning you should not have to think much about it. The simplest your problem is, it's also meaning the simplest you can find your issues and the less problems you will have. Just remember, just because you can doesn't mean you should, but if you have to, then we will give you the tools. Thank you very much.